All right, so I want to run through with you a couple of properties here that are hopefully things that you observed as you went through the math space practice, okay? But there's a couple of things, number one and number two especially, if you can get these down in your head really well, they will especially help you when you're graphing, okay? Because these two will help you find a point that's consistent basically on every graph, at least every parent function. You'll notice here that our parent function, if you remember, was y equals the log base something, so we'll put log base a of x. So the argument is your x coordinate, what it equals is your y coordinate. So in this case, number one, we see that anytime we plug in a 1 for x, we should get a 0 for y. Okay? So in other words, we're getting the point 1, 0 every time, no matter what the base is. And that's because, notice, if I rewrite that as an exponential, like you saw in the math space exercise, this is why I gave you a number of those to practice with. The base of your logarithm becomes the base of your exponential. So we're raising a to the 0 power and ending up with 1. Okay, because anything to the 0 is 1, unless it's 0, but we know a base of a logarithm can't be 0. Okay? Likewise, number two, if we think about this, this is saying the base a raised to the first power, of course, has to equal a, because anything to the first power is itself. All right? So, a1 will always be a point on the graph, unless it's stretched or moved around or anything like that. Okay? If you can get these 2 points, then graphing these is super easy. Okay?
1, 0.
Does that make sense? Any questions?
For only if the situation is where the base is the same as the, I don't know what it's called.
The base of the log is the same as the base of the exponent? What about that?
That's the only time that applies, right?
Well, no, that applies all the time. What we just said here applies all the time, no matter what the base is.
It's like if you take log base 10 of 10, it's 1. Because
It's
whatever
10.
the base, like, okay, log base 10. It's whatever power you raise 10 to get 10. And you raise 10 to the first power to get 10.
Mm-hmm.
Right, so is your coordinate times 1?
Well, what you're doing here is a to what power will equal a? Well, a to the first power will always equal a.
So it's a comma 1?
So it's a comma 1, yes.
Okay.
That's your point. Now, what number 3 shows us here is the fact that these are inverses of each other. Okay? The log base a of a to the x equals x. And a to the log base a of x power equals x. If you remember, when we were defining an inverse function, what does f inverse of f of x have to equal?
X.
X. It's got to equal x. And then also it has to work the other way. F of f inverse of x has to equal x. Okay? That's the definition of an inverse function. And that's what this property here is showing us. Okay? Now, if you think about it here on the bottom, the log base a of a to the x equals x. How do we know that's true? Because this is the language that you need to get used to. X is the exponent of our base a that will yield the argument a to the x. Okay? So a to the x power equals a to the x. All right? Really, it's just rearranging it from a logarithmic to an exponential. And then same thing, if you think about, the other one there, a to the log base a of x has to equal x. Okay. You'd have to take the log of both sides, and that one's a little more, we have to use some properties we haven't quite looked at yet to prove that side, but it works that way as well. Okay? So that right there is really showing us that the log and the exponential are inverse operations, as long as they have the same bases.
So 3 and 4, or just, is that for 3?
That's number 3. Number 4 is actually something we're going to use a lot in solving the equations, and that is if you have logs on both sides of an equation that have the same bases, then what you're taking the log of must be equal. For example, if I have the log, let's make it interesting, the log base pi of 3x minus 5 equals the log base pi of 7, okay? It doesn't matter that it's kind of weird to have a log base pi. They're the same, so I can just say, hey, 3x minus 5 has to equal 7.
And like the operation to get rid of that log pi would be raising it to pi, correct? To like cancel it out?
Basically, you're raising
The whole
pi to these powers,
Right,
yeah.
okay. I remembered that from other two, wanted to make sure that was correct.
Yeah, basically what you're doing is you're making it pi to the log base
Yeah.
pi
And that
of
cancels
3x
out
minus
that.
5, yeah. And that cancels, leaving just the
Is there any
3x minus
theorem?
5.
Is that like a theorem or something, or?
Well, that's, really, if you think about it, that's number 3.
What did you say? There's like a specific name for it.
I can't get rid of that. Anyways, okay? Now, let's start looking at the graph here. Let's start with this one, f of x equals log of x. All right, what's my base in this case?
10.
10, all right, this is our common logarithm. Okay, this is our common logarithm. Log base 10, we don't have to write it in there, but we can see it. Okay, so let's start graphing this. What's one point that's going to be on our graph? 1, 0, okay? It's going to be 1, 0 because if we think about this, if I plug in 1, log base 10 of 1 equals what value of y? Well, I know that this has a base of 10, so I could rewrite this as 10 to the y power has to equal 1. Well, the only thing I can raise 10 to get 1 is the 0 power. So that's 1, 0.
So unless they have like, some plus whatever, it's always going to be, they're always going to have 1, 0.
Yes, yeah. Another point. What's another point that we could have in this case? 10, 1, okay? If I make log base 10 of x equal to 1, then if I rewrite that as an exponential, it says 10 to the first has to equal x. Well, that's just 10. So there's our point 10, 1. And now I have this second point on my graph here. Okay? And this doesn't get up to 3 until we hit 100. So this is increasing, but increasing really, really slowly. Okay? So now that we have this, we can graph this. What do we know about, what's our domain for the log function? What?
0 to infinity?
Okay, can it equal 0?
1 to
Oh, it's 1.
Well, it could be between 0 and 1, but...
0 to infinity, not including 1.
Okay, good. Our domain here is going to be like this, or you could just say x is greater than 0, okay? Which means that x equals 0 is a what?
Asymptote.
It's an asymptote, okay? That's our vertical asymptote. Alright, so there's our vertical asymptote. If we want to sketch this, this one is tough to sketch. Alright.
How do you know that was an asymptote?
Well, because x cannot be negative, and it can't actually equal 0, but it can be everything right up to 0. Okay? That's one of the things we looked at on Friday when we were just talking about the graphs in general, or on yesterday. So, there you have that. By the way, just to make the connection here, and we'll look at another example and then tie it all together. Remember, we said the exponential was the inverse function, okay? If I had, let's say g of x is 10 to the x power, remember that has a y-intercept, or I'm sorry, it has a horizontal asymptote at 0, right? It has a y-intercept at 1, and when x is 1, y is 10, right?
Yeah, when 0 is.
How does this graph relate to the graph of log base 10 of x?
Reflected over here, reflected across y equals x.
There we go. It's reflected across that line y equals x. There's our line y equals x, and remember that's the case anytime we have an inverse function. It's going to be the reflection, okay? So keep that in mind there. You have the point 1, 0 on your log function. You've got the point 0, 1 on your exponential function. You've got the point a1 on your logarithmic function, where a is the base. And you have the point 1a on your exponential. All right, all the x's and y's are switched. Okay? All right, another quick example here on 2, and I'm actually going to go change my scale a little bit to make this one look a little nicer. Okay? Someone give me a point on this one. If g of x is log base 2 of x.
1, 0.
1, 0. Okay, good. 1, 0. That's always a point. And then what's another point?
Yeah.
It's
Why is it
that
always a
2,
boy?
1.
I know
Be-
we talked about it before, like
'cause-
in up in the directions, but I'm still like a little bit confused.
Remember, your y coordinate is the power. Anything to the 0 power is
1.
1. So anything to the 0 power equals 1. So 1, 0 is going to be a point on your graph every time, as long as it's not transformed somehow. Okay. And then what's another point?
2, 1.
2, 1, okay? The log base 2 of 2 will equal 1, because 2 to the first equals 2. Alright, so there's our point, 2, 1. I'll put that there. Anyone else give me another point that's on here? 4, 2. There you go. 4, 2 is also on here. Because 4 is 2 to the second power. So 4, 2. Alright. And then again we have that asymptote on our y-axis. Okay? Any questions? Comments?
You're gonna like kill me, but like I still don't understand like why these random points. Like I'm just having such trouble grasping this problem. this concept.
The key to this whole thing is to understand that a logarithm is an exponent.
Okay.
You've got to get that into your head, and that makes the whole universe here easier to handle. What exponent of 2 gives us 1? You know? Or what exponent of 2 gives us 0? Well, you can't. Alright, that's why we have the asymptote.
Are we always going to be doing 1 and 0? Like trying to find what exponent gets 1 and 0?
Well, that's the easiest way to do it because it's always going to be 1, 0, and it's always going to be whatever the base is, 1.
Yeah. And anything like 2 raised to the first power is 2.
Yes.
Oh, so you
And that's why here we have the point 4, 2, because 2 to the second power is 4. And our next one is going to be 8, 3, because 2 to the third power is 8. You know? If it helps you, here's the thing, guys. When you're graphing this, if it helps you initially, you can rewrite it as an exponential. I could rewrite this function as 2 to the g of x power has to equal x.
So for the graph above, will the next going to be 102?
Yes.
Okay.
Yes. Okay. So, looking through this, let's look at kind of the common things here. Alright? The domain and range, notice they are switched from what the exponential function was. The exponential, the domain was all real numbers, the range was greater than 0. Here, the domain is greater than 0, the range is all real numbers. Okay?
So why can the range, why can the domain never be, wait. Yeah, why can the domain never be, you can never plug a negative number in?
No, because if I have the base, notice right here, the base always has to be something greater than 1. Okay? And in any logarithm, technically speaking, you can have a base that's a fraction, but it has to be between 0 and 1. Alright? But in order for all of these things to apply, it has to be greater than 1. You can't have the base of a logarithm be a negative. So if you're raising a positive value to a power, you're never going to get a negative number, right? So you can't have a negative in your argument because it doesn't matter what you plug in, 10 to any power or 5 to any power
Oh, times a negative.
will never give you a negative value in the end. Okay? So, alright, so the key points here, your domain and range. Your x-intercept will always be 1, 0. Okay? Remember that. And also, remember that you have the point... oh, they don't have it on here. You always have the point somewhere that is the point A1. Okay? Another thing here, just to reiterate, a reflection of the graph of f of x equals a to the x in the line y equals x. That's what tells us it is the... No?
That was a shot in the dark, I'm not gonna lie.
A reflection across the line y equals x. It's the inverse. Okay? Alright.